Hello, I am Dr. Ellerby and I teach organic chemistry at UNE. In this video, we're going to go over how we can see the chair and boat conformations in cyclohexane. Conformations are the shapes of molecules. Cyclohexane has two specific shapes that have names, the chair conformation and the boat conformation. In this video, we'll take a look at why these names are used and help you be able to see them in a model. First, we'll look at the chair conformation. Here's a photo of a chaise lounge. Notice the flat part of the chair, and that's where you sit. And then here is the part for your back, and here is the part for your legs. Now I'll draw the shape of a chair on top of the image. And I make sure that the part where you sit is flat. So it's the red lines here, and I'll go over them. We start here in the middle, and then we continue along here, and down, and back up, and that's our abstract chair. Now I'll put the carbons in at the intersection of lines, just as I would do when adding detail to a line formula. So now we have 4 carbons forming a flat area, and the other 2 carbons at the top and the bottom of the chair. In this one, the carbons are marked on the chair, and in this one, I have removed the chair, just leaving the structure. Sorry about the inexactitude of the lines, but that's all my program will let me do. Here is the chair conformation in a model. Here is the upper carbon. I'm holding it by the lower carbon, and here are the 4 carbons that form the seat. To help you see the chair in the model, I'll number the model and the formula so that you can match up the carbons. So here's 1, there's 1. Here's 2 and 3, here's 2 and 3. That's 4, that's 4. 5, 6, 5, and 6. And that's how you see a chair in the chair conformation of cyclohexane. Now, what about the boat conformation? Here's a photo of a canoe. The canoe is pretty flat here in the middle, and it's got a prow at both ends that rises slightly. Now let's draw an abstracted shape. We start at the prow, move down, then along the flat place, and then start up. Start down, along the flat place, start up. Now, as I did before, I'll add the carbons at the intersection points of the lines. 1 here, 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 and here. Here is the image with the carbons in and with the extraneous boat parts deleted. Now, this figure shows the canoe deleted, and that's why this conformation is called a boat. Here's the boat in a model. I'm holding the model at one of the planar carbons with the 2 prows up. Now, to help you see the chair in the model, I'll number the model and formula so you can match up the carbons. Here's 1, here's 1, 2, 3, 2, 3, 4, 4, 5, 6, 5, 6. Here is a comparison of the boat and chair conformations of cyclohexane. To change from one conformation to another, we merely move the foot carbon of the chair conformation up from below to above the plane established by the 4 carbons. In other words, we take this carbon and bring it up, and that is now there. So these 2 conformations are changed into each other with the movement of 1 carbon. Of course, in a beaker of cyclohexane, we have all the possible conformations in that beaker because a beaker contains so many molecules. Chair and boat are simply names for the two of those conformations. At room temperature, the dominant conformation is chair. Just to point out, chair and boat are used for cyclocompounds. Staggered and eclipsed are used for linear compounds. For further help, particularly in placing substituents in axial and equatorial positions in rings, go to this Leah for Science video. That's it. Thanks for listening.